Welcome to Lecture 6 in our second semester on stochastic processes. In this lecture, we will discuss the connection between stochastic differential equations and Markov processes. And the basic statement of today's lecture will be that stochastic differential equations give rise to Markov processes, provided certain additional assumptions are satisfied. So we will consider basically the simplest type of stochastic differential equations in d-dimensional Euclidean space, which is of the form that dxt, that's the infinitesimal increment of the solution, should satisfy b, that it equals b of xt dt times sigma of xt dwt, which is the shorthand notation for the corresponding integral equation, which is the underlying concept for our notion of a solution of such an equation. And such an equation is typically also coming along with an initial condition, which in this case is some arbitrarily chosen initial point, deterministic point in the Euclidean line. So that's the kind of stochastic differential equations we want to consider in this piece of today. Note that these coefficients that we want to use here in this case will be just deterministic coefficients which depend only on the current position. What are these coefficients? Well, B in this case is what we call a drift vector field. It's a vector field as a map from RD, from the state space, into the state space itself, which in this case is identified with its tangent space. And then there's this additional sigma function, which is a function from our state space into the collection of matrices of dimension d times k, where d is again the dimension of our space and k is an arbitrary dimension, which is coinciding with the dimension of the noise of this dw. The noise here, dw, is assumed to be the increment in this incremental or infinitesimal writing. This noise is here in this particular case assumed to be a k-dimensional Brownian motion. And below, and basically for the entire segment of this class today, we will assume that these matrix field sigma and the drift vector field B satisfy a global Lipschitz condition, which means that if we evaluate the vector field B at two different locations and consider the difference, or if we evaluate the matrix field sigma at two different locations and consider the difference, then each of those differences is basically bounded by the difference of the corresponding points where we do these two separate evaluations, and there is a certain constant which provides then the upper bound. So that's the typical Lipschitz condition that we shall assume throughout this lecture. Okay, so that's the kind of stochastic differential equation we want to consider, and we will find out that solutions of such stochastic differential equations give rise to Markov processes, which then makes the connection to the theory that we have developed up to now in our second semester. So recall what we understand by a solution to such a stochastic differential equation. We start out with a k-dimensional Brownian motion, which is defined on some probability space omega fp. And if we have another process which is defined on the same probability space omega fp, then we call this second process x a solution to that stochastic differential equation if for almost all trajectories the following integral equality holds true for all times t. Namely, we want to make sure that x at any time t can be written as the initial position, which is little x, position in Euclidean space, plus the sum of the two stochastic integrals which capture the total amount of infinitesimal shifts or steps that the trajectory has taken, where the two stochastic integrals that appear here are, on the one hand, a classical integral with respect to the dt or ds integration variable, so that's the usual integral version. This alone, if the sigma was 0, this alone would be the conventional way to write a solution of an ordinary differential equations by means of the corresponding integral equation. But since we're dealing with stochastic differential equations, we have an additional term, which is the corresponding integral, which involves now this sigma vector field or this sigma matrix field, which is integrated against the realizations of the trajectories of these Brownian paths, which are the driving signals, or which is the driving force of this stochastic differential equations. And here I have written this integral of this matrix field with respect to this vector valued Brownian motion in the following form. Namely, I have written this matrix sigma, which is in fact a sigma ij. I have written this as a collection of column vectors, which are written as sigma 1 with an upper index sigma 1, sigma 2, until sigma k. In this case, I have k of such column vectors, where each column vector is a vector of dimension d. And this integral of the sigma against the Brownian motion of dimension k is to be understood that each component of this k-dimensional Brownian motion w is then integrated, or each of these individual components is taken as an integrator for the corresponding column vector of dimension d for the associated index j. So I'm doing all these integrations of this vector valued stochastic process against this scalar valued stochastic process, which is the increments of this corresponding Brownian motion in that respective dimension. That together, or that full integral produces, if I evaluate that integral at a certain terminal time t, that produces a vector of dimension d. And I do that for each of those possible choices of indices where the index runs from 1 to k, since I have k different components for the driving signal, and since I have k different column vectors for the matrix, I do this integration of the corresponding component against the corresponding vector valued component of the matrix field. I do that k times, and I take the sum of these vectors, which altogether produces me a random vector of dimension d, since it's some sort of a linear combination of vectors of dimension d. So altogether, this sum here on the right hand side is a sum, including of course the initial condition. This is a sum of different vectors of dimension d, which altogether of course then is a vector of dimension d. And I want that this sum of these stochastic integrals and any time t equals the value of that stochastic process x, which is at question. And let us emphasize once more that in these integrals, of course, what enters is the trajectory that the process x has realized so far. So we have, as you might recall, more or less the classical definition of a solution of an ordinary differential equation that you remember from your first years of education, but now with an additional component, which is this collection of stochastic integrals, which account for the additional randomness in the problem. So if this integral equation is correct for any time t, for almost all realizations of the trajectories of this process x, then we call this process x a solution to this stochastic differential equation. And we have a stronger concept than just being a solution. We also have this concept of a strong solution, which will be the concept that we will use in the current lecture, which is the case if that solution is moreover a process which is adapted to the filtration which is generated by this input Brownian motion. So this input Brownian motion, we shall also sometimes call it the signal. And if we, except for the existence of this process that satisfies this collection of integral equations, if we have such a process, and if additionally at any time t the process xt is measurable with respect to the sigma field generated for the corresponding time by the signal process, then we call this process, the solution process, even a strong solution. And that shall be important for the proof of the Markov property that we shall give below, as you find out in a few moments. Okay, and as for the existence of strong solutions, we have had or we have seen a theorem in the previous lecture, which actually guarantees that such strong solutions exist. And these exist, for instance, under these Lipschitz conditions, which we have just emphasized or just pointed out. So the theorem that I want to use, and which is basically a theorem which we have discussed in the previous lecture and the previous semester, is the following. So if we have a k-dimensional Brownian motion on a certain probability space, and if we have a vector field B and a matrix field sigma of that appropriate dimensions, which both satisfy this global Lipschitz conditions, then there exists a pathwise unique and strong solution to this stochastic differential equation star for any initial position x, for any starting point little x. And moreover, we have the following moment bounds or integrability bounds, namely for any exponent p of any size larger or equal than 1, we find that the corresponding maximal process of the solution, but now the maximal process in the sense of norm, so we take the, if you like, the maximal process of the solution, which is obtained by looking at the norm, the Euclidean norm of this solution trajectory, and taking its pathwise maximum over a finite interval. And if we raise that number to the pth power and take the expectation of that, that number is finite for all positive or non-negative times capital T. We have seen this, or we have seen a proof of this theorem in, if I remember correctly, lecture 25 of the previous semester. And the significance, if you like, of this last assertion regarding the finite moments is, in our context, just to make sure that this process x is well defined at any point of time. It does not leave our state space RD, so this phenomenon of explosion of trajectories which accelerate to infinity or singularities in time, they do not appear. And moreover, this exponential, or so correction, these moment bounds of arbitrary power will allow us to compute expectations of observables of this process, provided these observables do not grow too rapidly. And this is the subject of the next concept, namely, if we have a test function or an observable which maps our states of our stochastic process, which in this case is, of course, the Euclidean space of dimension d. If we have such an observable, we call it a function of polynomial growth. If there is some function, if there is some power p greater or equal to naught, such that there exists a constant c, such that this function f is bounded by the evaluation of this observable f is bounded from above by basically the absolute value or the norm of the argument x to that power p, at least when the absolute, or when the arguments are far outside a certain compact set. This is expressed in this formulation. So it says that for large values of x, for large arguments of x, this function does not grow faster than this power of the function x in norm. Right, so we put this 1 plus thing here in front in the c in order to make sure that this condition puts no restrictions, or this requirement puts no restrictions on the behavior of the function on a compact subset around the origin. So a function is of polynomial growth if it satisfies such a bound for an appropriately chosen power p and an appropriately chosen constant c. And the interpretation of this, let me say it again, is that the function values of x do not grow faster than x to that power in absolute norm, in absolute value, at least for arguments x which are sufficiently far outside of a compact set. Okay, and for such functions of polynomial growth, given the moment bound that we have just discussed above in the previous theorem, we can then reasonably introduce a well-defined notion of an operator, which is deduced from the solution of the stochastic differential equation. Namely, given such an observable f, we denote by PTF, evaluated at x, the operation of evaluating the observable on the state of the trajectory at time t, and taking the expectation of that. So it's the average observation we do on the states of the solution of our stochastic differential equation when we start the stochastic differential equation at initial time in position little x, and when we do this whole evaluation at a certain time t. That is our operation of the p. This is the p operation on the function f evaluated at time t and at position x. Of course, this is reminiscent of what we have been doing for Markov processes in this semester, respectively what we have been doing for Markov chains in the previous semester. And we will show, of course, that this PT operation is in fact defines in fact a Feller semigroup transition, a Feller transition function. Okay, and now comes the relevant proposition that entails the statement, or the main statement of today already, that the solutions of such a stochastic differential equation are in fact Markov processes in the language that we have developed in the first couple of sessions this semester. It says that if the coefficients b and sigma satisfy this Lipschitz condition, and if the function f is of polynomial growth, the observable, then it is so that if we now take the conditional expectation of such an observable evaluated on the process at time t, but conditioned to the sigma field which is generated by the trajectories of the process up to time s, when s is less or equal to t. So if we compute this conditional expectation, then we will find that this is the same as if we do our p operation for the time that corresponds to the difference of these two time points of observation, applied to the function f, to this observable, when evaluated at the new starting point, which corresponds to the location of the process, at time s, which corresponds to the latest time point of observation, which enters into the definition of this sigma field. And since this right-hand side of this equality deals with information that is given by the location of the process at time s alone, we in particular conclude that this process xt is in fact a Markov process according to our terminology that we introduced. The proof of this Markov property of the solution x depends crucially on the fact that we are dealing with a strong solution. X being a strong solution, let me recall that once more, means that at any point of time s, xs, the actual random variable xs, is measurable with respect to the sigma field which is generated by the trajectories of this input signal up to time s. It in particular implies that the corresponding filtration which is generated by the solution process x is a subfiltration of the filtration generated by the signal process omega. Okay, that we shall use at the very end. But it also implies, through our abstract theorem of factorization, or factorization lemma in measure theory, that the random variable xs is an abstract functional of the realizations of the signal process. That's a consequence of the fact that the xs random variable is measurable with respect to the sigma field generated by the signal up to that moment of time. So if we include also the initial position of this solution to the stochastic differential equation, then we find out that there must be an abstract function whose particular shape is of no importance for the argument we want to make, but there is an abstract function that allows to represent the solution at time s as a map that takes as an input only the starting point of our solution. It takes into account the time at which we want to evaluate the solution, and it takes as an input only the realization of the input signal up to that moment of time when we do the evaluation. That's what this strong solution brings about, the possibility to represent the solution as an abstract map from the input data of the solution. And that will be critical in the subsequent argument. In order to apply this possibility of representation, we make one more preliminary step. Namely, we choose two time points, s and t, and we choose an initial position x0, and we consider for the moment the realization of the solution when started at initial position x0 at the time s plus t. Well, we know that this solution satisfies a certain integral equation, and we can write down the corresponding integral equations for the two time points s and s plus t, and we can take the difference of these two integral representations of these two states of the solution of the stochastic differential equation, which boils down to saying that x, this solution at time s plus t, is the solution at position s plus the aggregated increments that the trajectory has experienced in the time interval from s to s plus t. And these are, of course, aggregated increments which are coming from the deterministic or drift integral and the corresponding integrals, increments which come from the corresponding stochastic integral. So this equality here can be obtained, for instance, by just writing down the corresponding two integral equations for the two time points s and s plus t, and just taking the difference of these two corresponding integral representations, which in the end brings up these truncated stochastic integrals on this sub-interval. Okay, in order to conclude further, I allow myself to do a time reparameterization, or just do a shift with regards to this integration variable by moving these integrations to the time interval from 0 to t, which is something I can do at the expense of shifting the argument inside this stochastic, inside these two integrals with regards to the time parameter at which the trajectories are being evaluated. And moreover, I can convince myself that the increments that enter in the stochastic integral on the right-hand side here in the second component of my sum of two integrals, these integrals, or these infinitesimal increments of the Brownian motion of the signal which enter this integral equation, they will not be altered, they will not be changed if I just add to each of the trajectories the state of the trajectory at time little s. This becomes probably also evident if you look into the equation or the representation of the same equation above. What we do have here, well, here, if we look at this term here, this is the increment of the trajectory, or this term is the symbolic writing or the symbolic representation of the infinitesimal increments of the trajectory of the signal after the time s, or in the time interval from s to s plus t. And of course, this infinitesimal increment, or this moves of up and down pushes of this increment, will not be changed if for each realization of randomness, each trajectory is shifted by a constant number, which here I choose to be the number of the trajectory at initial time, at the time s. So therefore it does not change whether I consider this stochastic differential equation with a w or with a w shifted, or the trajectory is shifted by the position that I observe of the signal at time s. And I call this new process, which is just a shifted version of our Brownian motion process, I call this new process W tilde. And it is important to note that this process W tilde, it features the increments of the Brownian motion after time s. That's something important to keep in mind. Now, considering this equation that I have just obtained and introducing a new process, x tilde, which is defined as my solution process, which I have just considered, but now for the times s plus t, where s is fixed and t is running over the non-negative reals. I see that this equation here just means that this x tilde process is a solution to my stochastic differential equation, which is defined through the vector field B and sigma as above, but now with the driving signal process W tilde, and which has the initial condition x s x naught, which is the position of the initial solution that I was starting with, but now evaluated at time s. And now finally I can bring in this abstract solution map, which we have just considered, which tells me that therefore the value of the x tilde process at time t must be obtained or can be represented as the application of the corresponding solution map that takes as an input the Brownian motion realization or the signal realization up to moment t, which is the W tilde process. It takes as an input the time at which I want to evaluate the tilde of the solution process, and of course it takes as an input the initial position of this tilde process, which in our case here is the position of the solution evaluated at time s. That's the important step. So the important step, let me say it again, is the possibility to write this solution, this strong solution, at any time as a realization of an appropriately chosen map that converts, there is a solution map that converts the driving signal and the initial condition into the actual position of this solution process. That is the important observation. And now, with this observation, we make the decisive step for the establishment of the corresponding Markov property. For that purpose, we take our observable f and we evaluate the observable on the process at times s plus t when it was started at initial position x naught. And we compute as a first step the conditional expectation of this observable given the sigma field which is generated by the signal process at time s. Well, we have seen that this x naught s plus t process, by the definition of our twiggle, is nothing but the x twiggle process, or the tilde process, evaluated at time t. So as an intermediate step, I just replace this, if you like, as the conditional expectation of the x tilde process, but evaluated at time t, when which enters here this conditional expectation, which is taken with respect to the sigma field generated by the signal process at time s. Okay, but we have just observed that this twiggle process can be represented through this solution map, phi. So therefore we insert this representation of the Twiggle process by means of this solution map. And now we have written this conditional expectation as an interesting object, which is an abstract function. If we look into in the interior of this conditional expectation, we see now that the conditional expectation that we want to compute involves only two nicely decomposed random elements. One is the value of the solution process at time s, and the other one is the increments of the trajectories of the signal process after time s. And now we use the independence of the signal process, which is the Brownian motion, the increments of the signal process, in order to convince ourselves that all the information in the sigma algebra, which is generated by the trajectories of the signal process up to time s, and the increments of the signal process for all times after time s, they are independent by our axiomatic properties of Brownian motion. So therefore, the process, or the information, or basically, yes, the process that is considered in this second component, or the second argument of this functional, is independent of the sigma algebra onto which we want to do the conditional expectation. And therefore, this conditional expectation is just a plain expectation. I should also mention, of course, that this random variable, which is in the first argument of this combined evaluation, this is, of course, measurable, again, by the property that x is adapted to the filtration generated by the signal process. So therefore, this guy, xs, is measurable with respect to that filtration, or with that sigma algebra. So therefore, by independence, this expectation that we want to compute, this conditional expectation, is just a plain expectation with respect to this second independent component, which is an expectation with respect to our solution map. But the expectation with respect to our solution map is just exactly the expectation according to the definition of the PT operation when evaluated at initial position that corresponds to the solution of our stochastic differential equation. In order to understand this last step and the importance of this phi map a little better, I would like to recall to you the following elementary statement about conditional expectations which involve independent random variables or independent random variables in sigma algebras, which is, for instance, the following statement, namely, if you have two independent random variables, say x and y, and you consider a function h which depends on those two random variables, which are supposed to be independent, and if you want to compute the conditional expectation of this combined measurement of x and y, conditional on the sigma algebra which is generated by one of the two, say x, then this conditional expectation is in fact just a plain expectation with respect to the remaining randomness, which is the remaining randomness in y, when you fix the first coordinate on which you take the conditional expectation as a certain fixed number x and evaluate that full expectation with respect to y alone at the value which you obtain when you fix the first coordinate to be equal to the realization of the first random variable. So a conditional expectation of a joint measurement of two random variables, conditioned of two random variables which are independent, conditioned onto the realization of, say, the first independent random variable, is nothing but taking a full expectation with respect to the second independent random variable evaluated with respect to the first argument on the realization of the independent first random variable. This is a straightforward consequence of the definition of conditional expectation, is what you would also assume to be hold if you think about it. And we use exactly this abstract or general principle in the previous argument as follows, which I have written now in a slightly different fashion. So recall that we wanted to compute the conditional expectation of this F evaluation when applied to this combination of the solution map, now evaluated at input datum XS for the new starting point, and evaluated on the realizations of the trajectories of the signal process up to time t. And we have argued that this second component, W twiggle, is independent of the sigma field onto which you take the conditional expectation. And this argument here on this side is measurable with respect to that sigma field. So therefore, doing this conditional expectation is just as good as if you fix the coordinate, the one of the two coordinates onto which is associated to the sigma algebra on which you take the conditional expectation, and then you take just the full expectation with respect to the second independent component, which is all the randomness, or which contains all the randomness which is left once you realize, or once you fix the sigma field here. And then, of course, evaluating this full expectation with respect to the second variable at the corresponding state for the first coordinate. This is what I wrote here in total analogy to the previously stated abstract conditional expectation property. But if you take a look at this expectation here, you see that this is exactly an expectation that involves our solutions, our solution map. So therefore, this expectation here is nothing but exactly the application of our PT operation to the function f, evaluated at this fixed location z, where again z needs to be equated with, needs to be equal, or needs to be set as x naught, which by just a definition of which we find then to be PT evaluated at this random location. So hence we have obtained this reduction of this conditional expectation, and we have managed to smuggle in this PT operation, which was basically the claim of the proposition that we want to show. However, there's a little thing left to be done, because here we consider the conditional expectation given the filtration generated by the input signal, and we want, as a matter of fact, to consider the filtration which is generated by the Markov process alone, but that can be dealt with by a standard argument, which is this. So ultimately we want to consider conditional expectations which involve the filtration or the sigma fields generated by the process X alone. But again, since the process X is a strong solution, so therefore it is adapted, and therefore the sigma field which is generated by the X process is a sub-sigma field or sub-filtration. If we want to compute that conditional expectation here, we can do it by first computing the conditional expectation of the same random variable, but conditioned on a sigma algebra which is finer, which in this case we choose to be the sigma field generated by the signal process. Okay, and in this inner conditional expectation, or the inner conditional expectation is exactly the conditional expectation that we were dealing with just a second ago. So here we have the representation of this inner conditional expectation, which involves this PT operation, which is PT acting on F, evaluated at the location, or at the state of the solution process at time S. And now we have this expression here in the remaining outer conditional expectation, but here this outer conditional expectation is taken with respect to the filtration generated by the process. So therefore, that quantity inside, which is just a combination of a certain function or an application of a certain function on the process at time S, that is of course measurable with respect to that sigma field. So therefore, the conditional expectation on that particular random variable has no effect, and we just get the random variable with no changes. And hence we finally arrived at this statement that we wanted to produce, namely that the conditional expectation of our solution map, of our solution process, which is observed by means of a certain function f, is the same as the PT operation on f, evaluated at that position that we observe at the latest according to this sigma field. This is exactly the Markov property of our solution process. And it was absolutely critical to make use of this representation of the solution by means of this solution map, which is a way to decompose future and past, which basically is a device to separate the future from the past, which are independent in case when we consider plane Brownian motion. And by means of the solution map, we have obtained the possibility to shift this mutual independence of future and past, which is originally encoded in the Brownian trajectories, to move or to migrate that kind of independence also to an independence property of the corresponding solution process. Okay, we have seen now that solutions to stochastic differential equations are Markov processes, basically in case when these solutions happen to be strong solutions. And now we want to argue that these Markov processes give rise to Feller semigroups or Feller contraction semigroups according to the systematic theory that we have developed so far. And for that purpose, we shall impose another restriction on the coefficients, namely, except for this low Lipschitz conditions, we want to impose now also for simplicity and to have a simpler proof that these two coefficient fields are also bounded. Then the PT, the family of PT operators, which we have introduced above, is in fact a conservative Feller contraction semigroup on the space of continuous functions on d-dimensional space which vanish at infinity. And we can give a partial characterization of the generator with little effort, namely the domain of the generator contains at least those continuous functions vanishing at infinity whose first and second order derivatives also vanish at infinity and are continuous, of course. This set of functions will be denoted by C02 of RD in the sequel. And we can write down an explicit formula for this generator in case a function has these regularity properties, namely the generator on such a function evaluated at a position x, that's the function which is obtained by computing the gradient of the function, f, the test function, and multiplying it in an inner product with a b, with a vector field. And then we have a second order part, as you would expect from Ito formula, which is 1/2 times the sum over all second order derivatives, partial derivatives, multiplied by a matrix Aij, by the entries of a symmetric matrix Aij, which is obtained by computing the sigma matrix field and its transpose, and taking the product of this. So this here can also be written as sigma times sigma transpose. It's just the product of these matrix with itself, but in the transpose, with its transpose evaluated at location, at indices ij. So that's the generator. That's the first hint towards the generator of this Feller diffusion. So let me say it again. The statement here is, if we have a stochastic differential equation whose coefficients b and sigma satisfy the global Lipschitz condition, and if moreover they are bounded functions, then the corresponding PT operation, which is this evaluation, or is the operation which converts a function and an observable into the average observation of the solution when started at a certain starting point x, then this family of operators constitute a conservative Feller contraction semigroup on our function space, which here as usual is the space of continuous functions which vanish at infinity. And we have at least the following partial characterization of the corresponding Feller generator. Namely, we can say that at least those functions that belong to our function space and whose first and second order derivatives in all combinations also belong to that function space, then these functions belong to the domain of the generator. And the generator on such a function produces the following function, namely, when we evaluate the operator, the function f after applying the operator at a position x, then this is the new function which is obtained, or the new value which is obtained by taking the inner product of the gradient of the function f with the b vector field and adding to that the weighted sum or linear combination of second order derivatives of that test function, where we have a prefactor as usual, we expect from Ito's formula of 1/2, and the weighted sum of the second derivatives is obtained by certain matrix entries Aij at location x, where the matrix Aij at position x is obtained by taking the product of the sigma matrix with its transpose at that position. That's the statement of the proposition that we are going to prove now. The proposition has two statements. One statement is about the fact that these PT operators form a Feller contraction semigroup on this space of continuous functions vanishing at infinity, and the second statement is a partial characterization of the generator of this process. We start by showing that these PT operators form a Feller transition semigroup. And one step here is to show that we have continuous dependence of the solutions to our stochastic differential equation, continuous dependence on the initial position, which will then entail that the PT operator, when applied to a continuous function, is actually a continuous function again. And for that purpose, we recall basically an argument which we have already made in the context of our solution theorem for stochastic differential equations which satisfy this Lipschitz condition by showing that we have a pathwise uniqueness under Lipschitz condition. And here we proceed in a similar fashion in order to show continuity, and we consider the solutions of our stochastic differential equations for two different starting points, x and y, which for simplicity of notation we just denote by x and y. And we want to show that in some sense, as we shall demonstrate below, we want to show that these solutions of these trajectories become close when x and y are close to one another. We do this by considering the difference process and by considering the norm squared of this difference process, which we hope is going to be small, provided x, the initial position, x is close to the initial position y. So this difference process as a difference of semi-martingales is a semi-martingale again, and it satisfies a semi-martingale decomposition which looks like this. So dz, so the infinitesimal increment in this infinitesimal notation, is the difference of the two vector fields evaluated at x and y respectively, multiplied with the dt increment times the difference of the matrix vector fields, sigma diffusion matrix vector fields as we call them, at these two different points of evaluation, multiplied by the infinitesimal increment of the signal. That's the infinitesimal increment of the z process. If we are then interested in the evolution of the z process in norm squared, we can apply the Ito formula to this norm squared process of the z, which is, of course, nothing but the inner product of z with itself. And if we hit this term with the Ito formula, this is nothing but a component-wise application of the integration by parts formula, or the Leibniz rule in this particular case, with the Ito correction. So the Leibniz rule in this case would say that this dz squared is 2 times z dz. So we get the 2 times the z times the dz, the infinitesimal increment of the z, but that has 2 parts, namely this increment with the dt term, and it has this stochastic increment, which is the difference of the sigmas multiplied by the dwt. So this part here, this first line of this Ito formula for the z process squared is the term that, or the formula, the part of the formula that you would expect from a naive application of chain rule. But then there is the Ito correction term, which accounts for the quadratic variation of the z process, which is to be understood in a component-wise fashion. And if you do the computation there, you will find that this term is then given by the trace of the difference of the sigmas multiplied with the difference of the sigmas transpose, which is a symmetric matrix, and we take the trace of that, and that needs to be multiplied with a dt term. That's a straightforward consequence of the structure of this noise, which is composed of component-wise independent Brownian motions. I will do that same computation basically a little later again, which will help you to understand why this term shows up. And so if we then write the same equation for the semi-martingale decomposition for this zt squared in integral form, and if we then apply the expectation operator to that, we see that everything that, or the term that accounts for the stochastic integral, will be a martingale, or at least a local martingale, and if you like, after a stopping argument or so, it does not contribute to the expectation. So therefore, after passing through the integral version of that equation and hitting that equation with the expectation operator, we find that e of xt minus yt squared is the xt minus yt in norm squared process at time t equals 0, which is of course the difference of the initial conditions squared in norm at the initial time. And then we get the two time integrals, which on the one hand involves the drift component, which was the first order term of our Ito formula, and then we have the second order term of our Ito formula, which involves these trace operators. And now we can make use of the Lipschitz continuity of the B vector fields together with the Cauchy-Schwarz inequality and the Lipschitz continuity of the sigma vector fields, the sigma matrix fields, which allows us to write each of those, or to give an upper bound at each of those time integrals by simply some constant, which basically is this Lipschitz constant that we had in the assumption, times the difference of the x process minus the y process, which then enters this integral squared, which enters then this integral. So that will be the estimate on the right-hand side. That estimate is correct for any t non-negative, which then by Grondwell's lemma tells us that this expectation is bounded from above by e to the c times, with a certain constant, e to the c times t times x minus y at initial time squared, which of course tells us that the solution at time t converges to the solution so the x solution at time t converges to the y solution at time t in L2, say, when x converges to y, because we just have this bound on the right-hand side for the difference in L2 of these two solutions. Okay, this tells us that the behavior of the trajectories as functions of the initial datum is continuous in this quantitative fashion, as we have stated here, and with a little bit of dominated convergence and standard arguments, it will also allow us then to pass to the corresponding continuity of this PT operators, because that involves, if you look at this PTF of x, let us look at that for x and y, possibly different. So writing out again what that actually means. PTF of x is the expectation of the observable evaluated on the position of the process at time t when starting x, and taking the mean value of that. Well, if x converges to y, we have seen that we have convergence of the x trajectories to the y trajectories in L2, so for a subsequence and so forth, it's going to be convergence almost surely, and since there is a unique limit, that convergence will even be correct for any such sequence, and with a little bit of dominant convergence, in case when the function f is continuous and is bounded, say, we can easily convince ourselves that we actually have continuous dependence of these evaluation operators on the initial position of the differential equation. So therefore, if we have a continuous function which vanishes at infinity, for instance, then this new function, which is obtained under this PT operation, that sends the function f into the function PTF, then this operation, then the new function is continuous. So therefore, the PT operators map continuous functions into continuous functions. That's one important necessity for a Feller semigroup on the space of continuous functions vanishing infinity. But what we also have to make sure is that we actually have a function of such kind which vanishes at infinity is continuous. Then we want to make sure that PTF is not only continuous, but we want to make sure that PTF is also a function which vanishes at infinity. That's what we also have to make sure, because we want to make sure, after all, that the PT operator is a self-map, is an endomorphism of this function space that we consider in our theory. Okay, for that purpose, let us consider, so we want to make sure now really that PTF is small if x is sufficiently far out of a suitably chosen compactum. So let's consider PTF for such a function which is vanishing at infinity. Well, then this PTF at x is, of course, bounded from above by the supremum of all functions values of f for all those y points which are in our neighborhood of the position x where we start. That's one part of this expectation. And the second part of this expectation that is underlying the definition of PT can be estimated by the infinity norm of f times the probability that at time t we find ourselves in a position which is from the starting position x farther away than r, than this value r, where r is an arbitrary positive constant, which is to be chosen a little later. So recall, probably I should add this. So PTF, let me probably make this comment. So PTF of x, recall again that this is just the expectation of f of x tx, and this expectation, in order to arrive at this inequality here, this expectation will be decomposed into an expected value over two sub-events, or two events which are mutually disjoint, namely either the trajectory is still inside this R ball of the starting point, or the trajectory has left, or at moment t is not inside this R ball. So it's the same f of x tx and so forth, but this will be when the trajectory is outside of that ball. And this decomposition into these two sub-events is the decomposition that we use for this bound on the right-hand side, namely the case when the trajectory at time t is still, or is inside this R ball, That's the case that we consider for this estimate when we replace the f function on this event just by the supremum, by the local supremum of the f function in this neighborhood of the x point. And the other case, the complementary case, is then estimated by the infinity norm of f times the probability that the trajectory at time t is not in the r ball. Well, if x, the position at which we evaluate this semigroup or this PTF, if that x position is very far out, then of course the value of the function f is small, as small as we want, in fact, provided that that x is chosen far out. And so also, if you like, by uniform continuity, for all y which are close to that x position, this number is really small. So therefore, if x is really small, the first number here can be made arbitrarily small. And what needs to be considered in the end is only the probability that for fixed time t, the process is outside the r ball of the initial position x. Let us derive an upper bound for this probability that the process at time t is further away, or at minimum a distance r away from its initial position x. First step is to apply Chebyshev's inequality, which allows us to estimate this probability by 1 over r squared times the expectation of this difference squared. But for this difference squared, we have a precise representation through a sum of two integrals, because xt is a solution to our stochastic differential equation. So if we insert exactly the representation of xt in terms of these sum of these two integrals, we obtain this sum of integrals in the norm squared. And by Cauchy-Schwarz inequality, we can estimate this expected value of the norm squared of the sum by twice the expected value of the sum of the squares of the two norms. This is this step here. And we then have to estimate each of these two summands individually. We start with the sum that corresponds to the drift integral. Okay, so that's the expectation of the norm squared of this integral. This integral is a vector-valued integral, so therefore it is to be written as the coordinate-wise vector of the individual integrals. That's what I do here. And if we are asking for the norm squared of this thing, we just have to take these coordinate-wise integrals and have to take the square of these coordinate-wise integrals and sum that up with respect to the coordinates. But now inside this t integral, if you like, we can apply a Cauchy-Schwarz inequality with respect to the time integration, which brings about a t factor. And inside in another t integral, or the t integral, which involves the coefficient bi squared when integrated over that time interval. But since b is bounded, the whole thing is again inside. This is the integral over a bounded function, which at most is in order of magnitude t, which together with that t factor which we had in front altogether produces an upper bound in terms of a c times t squared. As for the expectation of the stochastic integral part, I first expand this stochastic integral into its d Euclidean coordinates by doing just the inner product of this stochastic integral with each of the standard coordinate vectors ei and multiplying that coefficient with the corresponding standard coordinate direction ei, and the norm of this object squared is of course nothing but the sum over all these coefficients squared, which is what I do here. In the next step, I recall that this stochastic integral of this matrix field against this k-dimensional vector-valued noise can be understood as the sum of the corresponding stochastic integrals that are obtained by integrating each of the corresponding column vectors of this matrix against the corresponding coordinate of the noise process. And if I do this expansion inside this Euclidean inner product, and if that expansion is then hit by the inner product in the ith coordinate, or the inner product with the ith standard coordinate vector, then this extracts of each of those columns exactly the ith entry. And so therefore the sum of these stochastic integrals for the columns after inner product with the EI produces this sum of the stochastic integrals of along the ith row of the matrix integrated in each component against the corresponding coordinate of the vector-valued noise. This sum is then to be taken with respect to the running index L ranging from 1 to k, where k is the dimension of the input noise W. And if I do the same expansion for the second factor, of course, I get the same expression, but now I have introduced another running index because these two running indices are different, which is now the index M equals, which ranges from the values 1 to k. And each of these corresponding row entries of the matrix is integrated in each of these sums, on each of these sums against the mth coordinate of the input signal W. Okay, so that's now the full expansion of this norm squared of the stochastic integral process. And if I pull out all the summations in front of the expectation, which is defined by linearity, I see what I have for each fixed choice of indices I, L, and M. I have the expectation of a product of two scalar stochastic integrals, which are stochastic integrals of certain matrix entry functions evaluated on the trajectory integrated against the Brownian input signal in coordinate L and M. And then I recall that the expectation of the product of two stochastic integrals is just the same as the expectation of the product of the two integrands when integrated against the bracket process of the two stochastic integrals evaluated at the corresponding time capital T. And now I can finally use my information or find out information about the structure of the input signal. The input signal is k-dimensional Brownian motion, so therefore the bracket of two coordinate entries of this k-dimensional Brownian motion, L or M, the bracket process of those two is 0 when L is unequal to M, and when L equals M, this is just the identity function as a function of T. So therefore, the summation with respect to the L and M parameters collapses to a summation over the diagonal when L equals M, and in this case I get the product of sigma IL times sigma IL again, which is nothing but the trace again of these matrix, which is obtained by multiplying sigma with its transpose. This is what I'm having here, is exactly, if I plug in the summation with respect to these indices again, I see that this is nothing but the trace of sigma times sigma transpose evaluated along the trajectory. But again, here again I can use my assumption that this matrix coefficients are bounded, which means that this total integral contributes to the order of magnitude of only a linear, which is only linear in t. So therefore this whole thing is bounded from above by a certain constant times t. That's the ultimate estimate that I want to have on the right hand side. So if I sum these two upper bounds for the two terms which appeared here on the right hand side of my estimate for this exit probability, if you like, then I find that the probability that at time t, the stochastic process is outside an R ball of its initial position, that this probability is bounded from above by c, by a certain constant, over r squared times t squared plus t. Hence, if I come back to my initial aim to argue that this function PTF as a function of x is vanishing at infinity, and inserting this into my previous estimate, I can conclude that the value of PTF at position x is bounded from above by the supremum of the function f in an R neighborhood of the position x plus the infinity norm of the function f times a certain function c over r squared times t plus t squared. That's the estimate that I wanted to see. And hence, if I give myself a certain epsilon positive, I can choose first a certain r radius such that this term on the right hand side is smaller than epsilon half, for instance, which is possible, because the c does not depend on r, f, the infinity term does not depend on r, and t is some positive number. So there is a choice of an r big enough that this whole total quantity is no bigger than epsilon over 2. And finally, I can, by the fact that the function f vanishes at infinity, I can choose a certain compact which is probably sufficiently big such that outside this compact, for any x outside this compact, the function at the position x together with all other function values in the R neighborhood of that function is no bigger than epsilon half, which altogether, if I plug these two epsilon halves into the estimate here, into this estimate, I finally conclude that for this choice of k, which will be a choice in general which depends also on the previously chosen R, with this choice of k, the function the function PTF assumes values no bigger than epsilon if x is chosen outside of this k. So hence I have finally managed to convince myself that if the function f is continuous and vanishing at infinity, then is PTF, which is nothing but saying that this operator PT is in fact an operator which vanishes, which maps from our function space of continuous functions vanishing at infinity back into that function space of functions which are continuous and vanish at infinity. Fortunately, the remaining axioms for a Feller semigroup are easier to verify. For instance, if we ask for the contraction property of these PT operators, we recall that PTF of x, of course, is nothing but the expectation of the observable f on the state of the process at time t. But since this is an expected value, a certain average value of realizations of the function values f, this can be no bigger than the supremum norm of f. That's of course true for any x. So in particular, the supremum norm of PTF is no bigger than the supremum norm of f. So hence our P operators are in fact contraction operators on this space of continuous functions with the supremum norm. The next thing we want to check is whether this semigroup is strongly continuous, which means that PTF converges to F in the supremum norm when t tends to 0. So we fix an arbitrary position x and consider the difference between PTF and f at that position. PTF is represented as an expectation value, and since f of x is a constant for that expectation, we could just pull it inside the expectation value. And now we do a decomposition of this expectation value in a similar fashion as we did just in the mapping property proof above. So we decompose this expectation into the two mutually exclusive events, that either the process at time t is inside a delta ball of its initial position, or the process at time t is outside a delta ball of its initial position. And if the process at time t is still inside the delta ball of its starting position, then the difference that we will evaluate of these two positions will be difference in points x and y, which are no further away than the given threshold delta. So therefore, on this sub-event, this difference can be estimated from above by the maximum of all such differences we can observe when x and y are no further away than delta. And on the complementary event, when x is outside a delta neighborhood of the initial position x, then we just estimate this difference of these two evaluations of the function f by twice the supremum norm of the function. Okay, and then the next step, of course, we just replace, for an upper estimate, we just replace this probability on which appears on the first summand by a 1, since it's a probability. And we obtain this estimate when in the second summand, for this probability, we introduce or insert the estimate that we have used a few moments ago, which tells us that this probability is bounded from above by a certain constant over 1 over delta squared times t plus t squared. Now, we know that the function f is from the space of continuous functions which vanish at infinity, so in particular it's uniformly continuous. So therefore, for any tolerance level epsilon half, if you like, we find a delta such that the difference of two evaluations of the function f is no bigger than epsilon half, provided the two positions on which we evaluate are no further away from each other than delta. So therefore, choosing an appropriate delta small enough and fix it provides an upper bound of the first summand as epsilon half, say. Now, once the delta is chosen, we choose a t small enough such that 2 times f in the infinitum times c over delta, so that this whole expression for fixed delta and so forth is again smaller epsilon than epsilon half for all t smaller than that, which in particular provides an estimate which is independent on the particular location x where this was done, and hence we obtain that in fact PTF converges to f in supremum norm if t converges to 0. This is the strong continuity of this PT operators when t tends to 0. A trivial consequence of our definition of the PT operators is that they are all positive, namely if f is a non-negative function, then of course the PTF operation, which is some averaging operation of certain values of the f, is also non-negative. So hence it's a non-negative operator. And finally, the semigroup property of these PT operators follows directly from the Markov property, which is the usual argument. So if we evaluate PT plus S on f at position x, this is this expected value. But inside the expected value, we are allowed to inject an intermediate expected value onto a certain sub-sigma algebra, which doesn't change the global expected value. But here we can insert our Markov property as usual, which we had established at the beginning of this lecture or in the middle of this lecture. This thing here, which we have found there, we can write again as an expectation of a certain function g when it is evaluated now on the process at time s. where in this case the g has a particular shape, namely the g is just obtained through a transformation of the f under pt. But forgetting that for a moment, we just know that by our definition of the p operation, this is just, again, ps, the ps operator acting on the g function evaluated at position x, and recalling what the g actually was. G was the function which was obtained by applying the pt operator to the f. So therefore we get this nested applications of the p's, which we apply to, which we evaluate at location x. So in particular we obtain exactly the semigroup property that we wanted to see. Hence we have a semigroup of operators, and hence, if we haven't forgotten anything, we have finally really checked that all the axioms of a Feller contraction semigroup are satisfied in this case, and the first part of the theorem, of the statement of the theorem, is proved. We turn to the second part of the statement, which gives a partial characterization of the generator of this Feller contraction. The claim states that if the function f, or if a function f, which is of C2 regularity and vanishes at infinity, including all its derivatives, then this function is in the domain of the generator of this semigroup. And the generator applied to such a function is a partial differential operator, which involves the coefficients of this stochastic differential equation. Okay, so let us take such a function f of the stated regularity, namely suppose it's C2. Then we know that we can apply the Ito formula. So if we evaluate the function f on the process and compare with the evaluation of the function at the starting point of the process, then this calls for the application of the Ito formula, which then will bring up certain first and second order derivatives of the function. First of all, it brings about certain first order derivatives of the function, which are then integrated against the increment of the x process. And then it brings about all kinds of second order differentials of the function, which are integrated against the bracket process of the solution process x. And if you collect the terms properly, and you distinguish the terms which involve stochastic integrals with respect to the stochastic or the Brownian signal, and the terms which involve integrals against just the time, x time derivative or time increments, then you will find that exactly all the terms, collecting all the terms with a simple time increment or time integration, altogether constitute exactly this combination of first and second order derivatives acting on the function f, which appear in the statement of the generator A. And the only part that involves stochastic integrals is the first order derivative of the function f, which is then integrated against the transformed signal by means of this matrix field sigma. Hence, if I pass to the expected value using the fact that the function f is bounded together with all its first and second order derivatives, which allows me to pass to the limit after I use some stopping time and these expectations, I see that after expectation, or upon taking expectation, this stochastic integral term does not contribute to the evaluation of the expected value, which is the term, or which is the operation I need to do in order to compute the expected value of the PTF. In this case, so hence, if I take PTF of x minus f of x and divide by t, I end up with the corresponding expected value inside the ds integral of everything that's inside the ds integral. In particular, if I ask now, is it so that we have convergence with respect to the supremum norm of this difference quotient against the AF, then I can insert the representation of the PTF minus F over T that I have just obtained inside the absolute value here, which brings about this time averaged quantity of the AF along the trajectory of the solution, and the AF alone at the initial position, which I can all put into one big expectation, which then involves the expectation and this time averaging in one go. And again, using the uniform continuity of AF, which we know is again a function which is continuous and vanishes at infinity, it is easy to show that this term on the right-hand side converges to zero uniformly with respect to the position x, where I did this local evaluation. So in particular, I find that, as a matter of fact, such a function with the regularity of C2, when also together with the function its first and second order derivatives vanish at infinity, for such a function, this PT difference quotient at time t equals zero, or its difference quotient converges to this generator in uniform topology, which tells me exactly that this function is in the domain of the generator of this P semigroup, and that the generator has the claimed shape as a linear second order partial differential operator. Note that we were a little modest regarding the characterization of the generator in the previous theorem. We were just saying that certain functions, provided they have a certain regularity, they belong to the domain of the generator. But for the full statement, we would want to have actually a full characterization of this generator. And that is possible, at least in the case when this partial differential operator of second order is fully elliptic. By this I mean that this matrix which governs, or which is appearing in the second order operator, which is obtained by multiplying this sigma matrix with its transpose. So if this matrix A is uniformly elliptic, then we can actually fully characterize the generator of this semigroup. Recall first that I call a matrix elliptic if the corresponding inner product on Euclidean space that is formed by making use of A as a generating matrix for an inner product, if this inner product is strictly bounded from below by the Euclidean inner product with a certain strictly positive factor epsilon for all vectors in Euclidean space, which are non-zero. So the theorem that I want to discuss now, and I want to give two different proofs of that, is that if the matrix A, if the diffusion matrix, or the correction, if this matrix A that appears in the elliptic operator for my PDE, if that's a strictly elliptic matrix for all positions x, so I find a uniform epsilon such that this bound is correct for all x, for all positions x, then this set of functions which are twice continuously differentiable and which vanish at infinity together with its first and second order derivatives, then this is actually the full domain of this generator of our Feller semigroup. I want to give two proofs of this statement, and when we give a proof, you will see the strict interaction and the close interaction between analysis and probability theory at this point. The first proof of that fact, which will be the end point of today's lecture, uses PDE theory in order to give this result, which is a result, if you like, for a probabilistic question. So we use here, in this proof, we use PDE theory in a way to produce a statement about the stochastic process that we were considering. And we use PDE theory to give a proper and full characterization of the generator of the stochastic process. And how does that go here in this direction? So we use PDE theory now to import the following statement. Namely, if given a C2 function on d-dimensional space, we introduce the partial differential operator, which is not an operator in the strict functional analytic sense because we don't provide a full domain or whatever, but here we just give a formal partial differential operator, and we call it therefore only L in order to distinguish it from our generator of a semigroup. So suppose we introduce a second order partial differential operator which has the symbol L, by writing down exactly this formula that we have already stated in the formulation of the previous theorem, namely it's our formal differential operator that also appeared there as a generator. Then, and now comes the actual PDE statement, then for all lambda strictly positive in any function g which is continuous with vanishing at infinity, then there exists a unique function phi from the function space C02 such that lambda phi minus L phi equals g. So if you like, that's the import from PDE theory that we want to use here. The PDE theory tells us that if we have a partial differential operator of that type, and if the second order part, which is described through this matrix field Aij, if that is strictly elliptic, then for any given right-hand side, for any given right-hand side which has continuous, which is continuous and which is vanishing at infinity, then there exists a unique C2 function which then also vanishes at infinity together with its first and second derivatives, such that this function phi solves this partial differential equation where g appears on the right-hand side. That's a purely, in this way, if we write it like this is a purely analytical statement, and we could find that in any reasonable book devoted to PDE theory. It's the existence of global solutions for a certain elliptic partial differential equation, for which we then have some statement also about the decay at infinity of this solution. Okay, so what did we learn from that result, that we borrow from our colleagues from PDE theory? We learned from that in particular this function phi, since it is C2 regular and has these vanishing properties, this is a function which is in the domain of our semigroup generator. Because that's something that we have just already seen, right? So if you have a function which is so regular, then it's in the domain of the generator A. And we also know that the A operator on that function phi coincides with this PDE operator. Hence, we also know, just because it's the same thing, we know that lambda phi minus A phi equals g, because A phi for that particular phi coincides with L phi, which, in other words, tells us that this phi coincides with the abstract resolvent that is associated with our semigroup. So in other words, we used a PDE result in order to obtain explicit knowledge about the existence and the regularity of the resolvent for certain problems, for certain right-hand sides of our Feller semigroup. Now we want to use that in order to conclude that this is actually full information about the resultant. So, namely, take any function f which is from the domain of the generator. And we want to show now that this function must necessarily be in this set of C2 functions which vanish at infinity together with its derivatives. Okay, how do we conclude now? Well, we know that the function f is in the domain of the generator, so we are allowed to construct the function g as lambda f minus af, which by definition of our operator a, since it maps into C0, is again a function in our function space of continuous functions which vanish at infinity. But this g function is now a candidate to which we can apply our PDE result. Namely, invoking this previous PDE theorem, we know that there is a unique function phi such that lambda phi minus L phi equals g. And we have seen that for such a phi, this lambda phi minus L phi is the same as L phi minus A phi, which, on the other hand, since G equals LF minus AF by the definition of G, therefore must be LF minus AF. So in particular, we find that lambda phi minus A phi must be the same as LF minus AF, where both A and phi are in the domain of the generator. So in particular, we have that lambda times phi minus f minus a applied to the difference of phi minus f is the zero function. But the operator a is dissipative, which means that if we have a function in the domain of the generator which satisfies this null equation, then this function must be the zero function, which is to say that phi must be equal to f in this case, and which means that the function f must be, since that's what we have already learned from PDE theory, that the phi function is in this set of functions which are C2 regular and vanish at infinity together with its derivatives. So therefore the function f, since it's the same as phi, is in this space. So we have proved that if we have a function in the domain of the generator, then it must have this regularity property. And the other inclusion was something that we had learned already in the previous proposition, that any C2 regular function which vanishes at infinity together with its derivatives, that this is also in the domain of the generator. So therefore these two sets coincide and we have the full characterization of the generator. Right, so invoking PDE theory in this case for the strictly elliptic situation, we can actually give a full characterization of the domain of this generator, of this semigroup, and the theorem is completed in a way. There is also a very nice probabilistic approach to characterizing the regularity of these functions which are in the domain of the generator using explicit representation of the resolvent through the semigroup, and that is something that we shall discuss in the next 1 or 2 lectures. And the discussion will give us a very nice example of application of probabilistic techniques for proving actually analytical results, which are interesting. And that will be somehow paradigmatic for future arguments that we will discuss in the remaining weeks of this class.